Pluto is a remote and faint, more modest heavenly body that was once a part of the local star system. Despite this, recent and shocking statements by prominent space scientists Michio Kaku and Neil deGrasse Tyson have returned Pluto to public attention. They suggested that this far-off object might be on a probable collision trajectory with Neptune. They're not just speculating. They are advising that this small world could be on a dangerous, direct path leading to a terrible collision with Neptune. But how on earth could that occur? And what would the outcomes be if such a titanic event actually happened? Are we witnessing some kind of bizarre cosmic illusion, or is something significantly more real and terrifying hurtling toward us? Pluto's orbit cuts alarmingly close to Neptune's. Neil deGrasse Tyson and Michio Kaku are sounding the alarm. If things shift even slightly, we could be looking at a disastrous planetary mishap. Could Earth be in danger? And more importantly, how feasible is such a cosmic event? Accompany us as we investigate the possibilities and ramifications of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, continues to be a topic of fascination in the expansive cosmos as illustrated by current theories from top-tier analysts. Pluto's trajectory is dangerously close to Neptune's. Space experts Neil deGrasse Tyson and Michio Kaku are both warning about a conceivable hazardous interaction between these two worlds, which might suggest a tremendous risk to Earth. Still, how might such a scenario be achievable? Pluto's voyage around the solar sphere is unique to all others in our planetary system. Amazingly, it takes 248 Earth years to finish a full loop. Since its identification in 1930, it has yet to complete even one full cycle. But the curiosity doesn't end there. Pluto's defined trajectory is exceptionally elongated, deviating significantly from the mostly circular revolutions of the principal planets. What intensifies Pluto's extraordinary path is its tilt, which is 17 degrees from the solar plane. The route Pluto traces is significantly more irregular in contrast with other planets. This tilt and eccentricity add layers of complexity to its orbital pattern. Arguably, one of the most intriguing elements of Pluto's orbit is its overlap with Neptune's. For approximately 2 decades during each circuit, Pluto actually becomes nearer to the Sun than Neptune, contrary to what one might expect based on the conventional placement of the planets. This brings up the common inquiry: why hasn't Pluto collided with Neptune? The explanation resides within the effects of gravity from surrounding planetary bodies. The examination of Pluto's trajectory began shortly after its revelation. Initially, astronomical researchers tried to comprehend its unique route. Unlike most other planets, whose loops are relatively aligned with the solar plane, Pluto's route stands out with its sharp angle and uneven layout. The enigma deepened with the understanding that Pluto's orbit does indeed intersect Neptune's. The steadiness of Pluto's path, despite these irregularities, stands as evidence of the subtleties of the three-body dilemma in cosmic physics. Outer space entails figuring out how a trio of cosmic entities, like Pluto, Neptune, and the Sun, move and affect each other through their gravitational pull. It's akin to forecasting future movements based on original positions and mutual, gravitational tugs. In Pluto's case, this issue highlights how its motion, Neptune's loop, and the Sun's pull all operate in an interwoven way. The expressions asynchronous oscillation, orbital drift, and VZK wobble are essential for solving this mystery. As noted by astrophysics specialists, what ensures that the planets remain in their circular tracks is asynchronous oscillation. Regarding Pluto and Neptune, this phrase fundamentally means that when Pluto traverses Neptune's orbital path, it is situated at no less than a 90-degree angle away from Neptune. This angular separation is vital in preventing their paths from clashing. Orbital drift, by contrast, refers to a body's vertical movement as it revolves. For Pluto, this indicates that when it gets closest to Neptune or another giant world, it lies significantly above their orbital tracks, providing an added level of defense against likely crashes. An additional major component in this discussion is the VZK wobble, named for three researchers, Kaku, Zell, and Kai, who analyzed the spatial dynamics of cosmic entities, including how three astronomical masses like Pluto, Neptune, and the Sun exert pull on one another with their mass-based attraction. This influence shapes their movement. In Pluto's instance, the VZK wobble provides insight into why its route near the Sun appears so erratic. Although Pluto's movement seems unstable, this wobble aids in keeping it flowing smoothly across vast durations. The VZK wobble reveals that, despite how the universe may appear strange and erratic, principles and patterns continue to impose some degree of order. These dynamics assist in maintaining Pluto's steady course, ensuring it doesn't crash into Neptune or stray from its regular route. This tri-body interaction is crucial to grasping how space trajectories shift because of external forces. Analyzing it teaches us more about Pluto, our planetary group, and even far-off galaxies and their stars. Numerical projections in the late 1980s demonstrated that even though Pluto's orbit is reinforced by stabilizing attributes, it remains erratic. Small initial deviations can result in dramatic divergences over centuries. Still, these orbital behaviors have been proven to maintain equilibrium over astonishingly extensive timelines. Evaluating changes via later automated readings has helped us learn how the behemoth planets Neptune, Jupiter, and Saturn affect Pluto's revolution around the Sun. Neptune has its own unique orbital correlation with Pluto, in which, for every 2 revolutions Pluto performs, Neptune completes 3. This synchronized relationship helps preserve Pluto's stability. However, Neptune doesn't act alone. Jupiter's immense gravity also plays a role. Pluto plays a significant role in preserving its own consistent orbit. Saturn, as well, contributes to this balance. Research reveals that Jupiter's colossal mass is powerful enough to protect Pluto's path for an extremely long duration. It seems that Jupiter, Saturn, and Neptune are all working together to ensure that Pluto glides securely through the void without running into dangers. These strange yet essential systems play a major role in maintaining cosmic order. Without such mechanics, our solar neighborhood would be a far more turbulent realm. Objects like Pluto might collide with others or be ejected completely, setting off chain reactions with other astronomical entities, especially concerning Pluto, and its future interactions with Neptune. This requires an understanding of its motion, which provides a clearer picture of the planet's vibrant and ever-shifting nature. Pluto's example illustrates how even seemingly unstable paths can reach equilibrium through intricate gravitational and kinetic interactions. It also underscores the necessity for continuous monitoring and examination of such oddities to better comprehend where we fit in the universe. Delving deep into otherworldly realms frequently makes us confront the bizarre characteristics of heavenly bodies. Furthermore, Pluto's orbit is a perfect case of this irregularity. The theory of orbital disorder, which refers to the sensitive dependence of an orbit on its initial data, can be clearly seen here. This suggests that Pluto's minimal alterations in its coordinates or speed could greatly influence its far future path. Computer-based forecasting has been very successful and beneficial for space scholars working to decode Pluto's behavior. These programs employ elaborate equations to simulate how Neptune, Pluto, and other bodies interact gravitationally. By adjusting minor aspects within these forecasts, scientists can observe how even slight changes can result in completely different destinations. In the late 1980s, surprisingly, digital models revealed that despite Pluto's stabilizing mechanisms, such as asynchronous oscillation and orbital drift, its journey may still behave abnormally. If Pluto begins with even a very small discrepancy in location or velocity, its future position might look vastly different in just a few years. Yet, despite this unpredictability, Pluto's trajectory has endured across immense spans of time, spanning billions of years, indicating that its path has an underlying consistency, even though it may appear unruly at first glance. Predicting stellar orbits, particularly ones as inconsistent as Pluto's, remains a monumental task. At its heart, the unpredictability of these systems results in far future predictions riddled with unknowns. While mathematical models are outstanding for decoding and estimating cosmic motion, they also highlight our limits. These formulas depend heavily on starting values, and even a minor inaccuracy or alteration can significantly alter the outcome. Pinpoint accuracy is a real challenge. Beyond the unpredictability of planetary pathways, Pluto highlights the constant change and development of the universe. Although humanity has uncovered significant understanding of the stars, Pluto's oddities remind us how much still lies in the shadows. Deciphering how massive planets alter Pluto's movements grants us broader awareness of solar system behavior. It shows how each planet's presence and place can meaningfully influence the steadiness and direction of others within the structure. So why do astrophysicists suddenly express anxiety about a possible smash-up between Pluto and Neptune, even with all the cosmic laws acting to prevent it? Neil deGrasse Tyson, a well-known figure in the space science community and a key promoter of cosmic knowledge, delivers a distinct angle on our planetary mysteries, especially Pluto's peculiar saga. Tyson, recognized for his efforts in demoting Pluto to dwarf status, provides perceptive thoughts on the shifting principles of orbital research and the general public's curiosity about overlooked regions of space. His stance regarding Pluto's label in the heavens stems from our constantly improving understanding of the solar neighborhood. He views the shift not as an insult, but as a critical correction to our grasp of objects revolving around our star. Tyson's outlook on orbital physics places an emphasis on ongoing education and flexibility. He interprets complicated trajectories, like Pluto's, as a symbol of how much more there is to uncover. The mystery of such questions keeps astronomy thrilling. However, while Tyson remains hopeful, his outlook on a potential Pluto-Neptune collision is far less cheerful. His apprehension about Pluto's destiny, once a full-fledged planet, is rooted in his recognition of the erratic behavior of these orbital dances. He acknowledges that Pluto has thus far remained secure, but small changes accumulating over time might trigger disastrous events. Pluto's trajectory, particularly its area of overlap with Neptune, forms a complex spatial rhythm that may not remain in sync forever. In Tyson's perspective, even the slightest disturbances in Pluto's path could yield huge repercussions. If these imbalances persist and grow over millennia, they could eventually result in chaos or even a planetary crash. Such a development would not occur anytime soon. Instead, it would span unimaginable lengths of time, well beyond the reach of human civilization. Still, Tyson's cautious tone calls for further vigilance and deeper investigation into Pluto's orbital pattern. Tyson is not standing alone. Michio Kaku, a renowned theoretical physicist, also perceives the astronomical upheaval that might result from interplanetary interactions. Although Kaku matches Tyson's awe for the magnificence of the universe, he also recognizes the shaky balance of planetary orbits and the wild, unforeseen effects that may arise with time. Both Kaku and Tyson highlight the necessity of persistent space exploration into the invisible powers dictating planetary drift and the outlook for our starbound family. In the end, Pluto's situation illustrates how our knowledge of the universe is always changing and adjusting. Each breakthrough generates additional intrigue. As space science advances, the possibility of a Pluto-Neptune collision is a humbling reminder that outer space is packed with twists and turns, and even peaceful planetary paths can change drastically over time. These lessons from Pluto serve to remind us to keep pondering the skies incessantly and to keep questioning the secrets that the stars still hold.